Is working. Yay. All right. So today we're continuing our talk on probability, and we left off probability. Okay, hang on. Let me just say this. And then we'll flip back. What is going on? Computer, why do you do this to me? Okay, so we've got probability. We left off on Monday. We said we had the OR rule. And we said that if you got probability of A or B, we said this is equal to the probability of A plus the probability of B minus the overlap, the probability of A and B. Right. Okay, and so now we have a special case of this where we have something called mutually exclusive events. And we say that if two events, A and B, are mutually exclusive, then the probability of A and B is equal to 0. Okay? Meaning that the two events cannot happen together. The two events cannot happen together, or if one happens, then the other is impossible. Okay. And so if we have a situation where we have mutually exclusive events, then the probability of A or B becomes the probability of A plus the probability of B minus the probability of A and B, but the probability of A and B is 0, so this just reduces to that, okay? Probability of A or B equals probability of A plus the probability of B if A and B are mutually exclusive. I'm going to just abbreviate this as ME. Okay, if A and B are mutually exclusive, then it reduces to this. So let me just give you an example of a mutually exclusive events. So for example, we could talk about rolling a die. And A can be the outcome where the die lands on 1. And B can be the die lands on 4. Okay, these are mutually exclusive events. There's no overlap. There is no overlap where A and B can happen together. You cannot, probability of getting a 1 and a 4 at the same time when you roll the die, that's 0. Probability of A and B is equal to 0. So if we want to say what is the probability of A or B, okay, if A is the die lands on 1, the probability of A is equal to what? Assuming a fair die. 1 out of 6, yes. And the probability of B is 1 out of 6, okay? And so the probability of A or B just becomes the probability of A plus the probability of B. So we get 1 out of 6 plus 1 out of 6, or 1/3. What's the probability of rolling a 1 or a 4? Well, that happens with probability 1/3. All right, is this okay? On the other hand, we can talk about events that are independent. Independent events, okay? And we would say that events A and B are independent if the outcome of one event has no influence on the outcome of the other event. Okay, has no influence, or we can say it just has no association, has no influence or has no association with the outcome of the other event. Okay, and if there is an association, we say that those events are dependent. Okay, if there is an association, then those events are dependent. Okay, so I'm going to do a political example. I hope this doesn't bring up any bad memories. But we'll just say, okay, let's say we selected a random voter, okay, a random voter from who voted in the 2016 presidential election. Okay, so we will select a random voter who voted in the 2016 presidential election. Okay. Okay, and then so we could say, you know, what is the probability that this randomly select that we select someone who voted for Trump? Okay, so we'll say probability of Trump. Okay, well, this would be equal to the proportion of the popular vote that Trump won, right? So I looked this up earlier today. That proportion is 0.461, okay? So Trump won about 46% of the popular vote. So if we select a person at random who voted in the presidential election, this is the probability that of randomly selecting someone who voted for Trump. Okay, we can ask, all right, what if I gave you a piece of information? Okay, I'm going to give you a piece of information. Okay, and we say that, you know, I selected a person at random. And the person I selected is from California. And so now that we know this piece of information I've given you is that the person is from California, The question is, what is the probability that this person voted for Trump? Okay. Okay, and so is that the same as 0.461? No, because, and again, I looked at this information up earlier. In California, Trump won only 32.8% of the vote in California. So in this case, we would say the probability that someone voted for Trump, given the person is from California, is 0.328. Okay, so this is, we write this as the probability of voting Trump given the voter is from California. All right. Is this okay? Does this make sense? And so what we say is that because this number is different from this number, so knowing that somebody is from California will affects the probability that this person voted for Trump, or that's probably not changes. These are not causal relationships, but the fact that we know that this person is from California, the probability that this person voted for Trump is different than when we just selected someone at random from the entire nation. And so because there's a difference there, we say that there is an association. Okay, there's an association between the variable voting for Trump and the variable from California. Okay, and then if we found out that this person is from UCLA, then the probability changes even more. Okay, so because probability of Trump is different from probability of Trump given California, okay, we say there is an association between the events or variables. Okay. On the other hand, if we looked at something like, is somebody left-handed or right-handed, and who did they vote for, we wouldn't expect that to have an effect, right? So we could say, contrast this, to, probability of Trump versus probability of voting for Trump if we know that someone is left-handed. Okay. This number should be these two numbers should be the same, right? These two values should be the same because be the same. And if they're the same, that means being left-handed is independent of how someone votes. Okay. If we know someone is from California, that gives us some information about how they voted. Okay. I mean, of course, any individual you select, you don't know how that individual selected, but overall the probabilities change. Okay, probabilities are different. But if I tell you, if the piece of information I give you is whether someone is left-handed or right-handed, that doesn't really help you in terms of determining how someone voted. Okay, if these two values are the same, so and that means, left-handedness and and kind of voting for Trump is independent. And so during the election season, they said Trump is doing well among this demographic group. People with this education level, and people whatever. All of those things are, we would say, are associated with the outcome. Are associated. Those variables are associated. Okay, so to check if events are independent or not, events are independent or not, what we check is we check to see if the probability of A given B is equal to, so if they are independent, probability of A given B should be equal to what? The probability of A. Okay? So the probability of A, if we're given that B has happened, that should just equal the probability of A. So if the probability of A given B is equal to the probability of A, then A and B are independent. And if they are different, if the probability of A given B is different from the probability of A, then that means they are dependent, or that there is an association. Because we're saying that knowing that how someone voted, or if we know that B has happened, and if that affects the probability of A happening, then that means they are related somehow. Okay, let's just try a silly example here. Let's say we will select people. Either from California or Texas. Okay, so this will be variable 1. Variable 1 is whether or not the person is from California or Texas. Okay, and then variable 2 will be whether they drive a truck or not. Okay, I'm just playing on some silly stereotypes. Okay, drives truck or not. Okay, so we will say I'll set up a two-way table. I don't know if anybody here is from Texas. Please don't be offended by this dumb example here. All right, so we'll say either California or Texas, and drives a truck or no truck. Yeah. Okay, I'm going to just fill in some numbers here. We're going to say we have 120 people from California, 100 people from Texas, for a total of 220 people. I'll say 90 people drive trucks and 130 don't drive trucks. And I'm going to just say 35, 85, 55, and 45. Okay, let's make a clicker question. And the question here is driving a truck independent of being from Texas? Okay, and so your answer choices are yes, they are independent. B, no, they are not independent because, let me just check some numbers, because 55 divided by 220 is not equal to 90 divided by 220. Or C, no, because 55 divided by 100 is not equal to 90 divided by 220. And D is no, because 55 over 100 is not equal to 45 over 100. Okay, so basically what I want you to check is the probability of A given B, is that equal to the probability of A? Okay, and if they are, then they're independent, and if they're not, then they are dependent. But I want you to kind of check to find the correct pair of things here. Okay, so let me just start the session and we'll run the question. And if you want to talk to your neighbor about what the correct answer is, you can talk to your neighbor about the correct answer. And okay, and the poll is running. You can get your clicks in here. Yes, question. Yeah. Oh, okay. Yeah. Which one is A and which one is B? You're gonna have to try to work that out. And the truth is it doesn't matter, but I guess for this question it does. Yeah. I'll pause the video. Okay. Let's see. Okay, and indeed C is the correct answer. Okay, so here we just have to arbitrarily label one of these. I'll say truck is A and Texas is B. Okay, and so in this case we'll do probability. What is the probability of truck given the person is from Texas? Okay, well we say in Texas there's 100 people, at least in our table, we have 100 people total from Texas. So if we know someone is from Texas, what's the probability they drive a truck? That's going to be 55 over 100. That's going to be truck given Texas. Is that equal to probability of A, which we've called truck? Okay, we called truck A. And so is that equal? Well, the probability of truck overall is going to be 90 divided by 220. So 55 over 100 is 0.55. 90 divided by 220, I think, is 0.41 or something. 90 divided by 220, yeah, 0.4091. All right, these two are not equal, therefore they are not independent, they are dependent. Not equal, they are dependent. Okay. If you labeled truck B and Texas A, you'd get different decimals, but your conclusion would be the same. Probability of Texas given truck is not equal to the probability of Texas, and so you'd come to the same conclusion that they are dependent. Is that okay? I'll just quickly show you what that looks like. So if we did probability of, not truck, probability of Texas given truck versus probability of Texas. Okay, this is what we have to check. Probability of Texas given truck would be 55 divided by 90 versus probability of Texas overall, which is 100 divided by 220. Okay, and so 55 over 90 is 0.61, and 100 divided by 220 is 0.4545. Okay, they are not the same, therefore we conclude that they are dependent. Okay. Everyone's good? Checking to see if events are independent or dependent. Is that a question? How did it get like 55 over 90 or? Yeah. Okay. So here what we're doing is we're looking at the table. So for example, what is the probability of truck given Texas? Okay. So when we write this vertical bar, that means given. This is the piece of information that we have. This means, I selected someone at random. I find out this person is from Texas. Okay. So what this does is it eliminates it. It basically gets rid of this entire column over here. I don't know how to. Basically, it just reduces our world to just the column with Texas. Okay, so now our world, instead of having 220 people in our table, we now just have 100 people. And in Texas, we've divided you into either you drive a truck or you don't. So what is the probability that you drive a truck if you are from Texas? That's going to be 55 out of 100. And that's what we have here. Versus probability of driving a truck overall, here we don't care if you're from California or Texas. We just want to know what's the probability you drive a truck in general. We have a total of 90 people who drive trucks, total of 220 people. So we do 90 divided by 220. Okay, over here we're just looking at the row. If we know that you drive a truck, our world is reduced to just this row of 90 people. Of those 90 people, 55 are from Texas, versus in the entire table, 100 people out of 220 are from Texas. Yes?
So the answer in red is equally correct to the answer in blue.
Yes.
But if that person would have done it that way, they would have gotten that way.
Well, if the person did it this way, their answer choice would not have been available here, okay? And so they would have had to try out some of the other answers, okay? They would know that the answer is no, but then, looking at these other options, these are just not. The other options, B and D, are making the wrong comparisons. You're not comparing trucks versus no trucks, or this one is 55 out of 220. This is the overall probability of truck and Texas versus probability of just truck. Okay, so they might not have found this, and then you would have had to kind of switch them the other way. All right, so let me just kind of formally define this concept of a conditional probability. And so in a conditional probability, what we have is we have the probability of A given B. Probability of A given B is the probability of A and B divided by the probability of B. Okay, that's the probability of A given B. It's the probability of A and B divided by the probability of B. With a little bit of algebra, we can rewrite this to be the probability of A and B. If I multiply both sides by the probability of B, with a little bit of algebra, this can be written as the probability of B times the probability of A given B. Okay. The probability of B times the probability of A given B, that will be the probability of A and B. Okay, just rearranging some terms. It should be noted that probability of A and B is exactly the same as the probability of B and A. So how the probability of truck and Texas, that's the same as probability of Texas and truck, okay? The terms inside, which one you have first and which one you have second, that doesn't matter. That does not matter, okay? But basically what we're saying is that the probability of some event, A and B, a pair of events, A and B, in order to have that, B has to happen, and then we would multiply that by the probability that A happens if we know B has happened. So let me just kind of give you an example here. Let's say if there's a storm, we'll say the probability that, let's say you're at the airport, the probability of a delay, a flight delay, is 0.6. Okay? So the way we write this symbolically is we write the probability of a delay given the fact that there's a storm. Okay, so we say the probability of a delay given the fact that there's a storm. Over here we can say if there is no storm, then the probability of a delay is only 0.2. Okay, so how would I write this? This would be probability of what given what? Delay given no storm. Okay, it's not and, it's the probability of delay given no storm. Okay, so this is, I guess I'll write this. We read this as probability of A given B. Okay, this is how we read this. Probability of A given B. Okay, and then so, we check the weather. And it says the probability of a storm is 0.3. Okay, that's what we'll say. All right, so here's the question. What is the probability that when you go to the airport, you experience a storm, and on top of that, you get delayed? All right, so what is the probability you face a storm and there's a delay? Okay, well, this is going to be the probability of storm and delay, or probability of delay and storm, however you want to write it. And this is going to be the probability of storm times the probability of delay given that there's a storm. So it's the probability, first a storm has to happen, and then on top of that, there has to be a delay. Okay? Except that probability of the delay is not just the probability of a delay, but it's the probability of delay given the fact that there's a storm. So for this, we say, well, the probability of a storm, that's going to be 0.3, and we multiply that by what? 0.6, right? 0.6, because first there has to be a storm. That happens with probability of 0.3, and then on top of that, there has to be a delay. But the probability of a delay changes whether there's a storm or not. So we have to use the probability of a delay given that there's a storm. Okay, so when we multiply this out, we get 0.18. Is that okay? Let me try giving you another question here. And should I make a clicker question out of this? Sure. All right, let's try this out here. Okay. All right, so I will ask, what is the probability for the best case scenario here? Okay, what is the probability of having no storm and no delay? Okay, so you go to the airport, there's no storm, and then your flight is on time. Best case scenario. Okay, you can answer this question with the information that you have. Okay, you're gonna have to think of like the complement rule and things like that. Okay, let's give you some answer choices here. Okay, if you want to talk to your neighbor about this, you try this out. Probability of no storm, whoops, sorry. Probability of no storm and no delay. Okay, let's take a look, and that is the correct answer, D. All right, so what is this? This is going to be probability of no storm and no delay. So first we got to find the probability of no storm, and then we would multiply this by the probability of no storm, probability of no delay, given the fact that there was no storm. Okay, probability of no storm and no delay. This is going to be the probability of no storm times the probability of no delay and no storm. So if the probability of a storm is 0.3, then the probability of no storm would be 1 minus that, which is 0.7. Okay? And then over here, the probability of delay given no storm means that the probability of no delay, given the fact that there's no storm, is 1 minus 0.2, which is 0.8. So here I plug in 0.8, and we multiply these together, and we get 0.56. So that's the probability of no storm and no delay. It's the probability of no storm, which is 1 minus this, and the probability of no delay given no storm. So we just do, 1 minus the probability of a delay given the fact that there's no storm. So we just kind of reduce our world to the situation where there's no storm, and once we know that there's no storm, either two things can happen. There's a delay or there's no delay, and that's how we get 0.8. Okay, we'll end here. We'll see you guys on Friday for the midterm exam. Good luck as you guys study.